I at least want to talk about the binomial theorem and binomial probability distribution today, and depending on how long that takes, I might just stop there and do a slight review, or I'll finish chapter 13 and then do the review, depending on how quickly we get through this. So recall let me close these lines. Okay, so last time we spoke about the probability distribution. It's basically just a table that tells you the possible outcomes of some random variable and the probabilities of each outcome. Recall the probability distribution x, p of x, where this is x1, x2, xn, p1, p2, and has expected value mu equals to e x equals, what was the expected value? 1. No. The sum of the probabilities must be 1. It was just the sum of all xi times p I. Right, so it's x1 times p1 plus xn times pn. And this was pretty much the average, or the expected value of the distribution. We ended there last time. We did an example. I also want to define the standard deviation. If you're given a probability distribution, you can actually find it, the standard deviation of this. Also, standard deviation sigma sub x to denote that we're actually looking at the variable x is given by the formula. It's the radical x1 minus mu squared times p1 plus x2 minus mu squared times p2 xn minus mu squared times pn. Right. Remember, the Pn has the division by n part in it, so we can literally just multiply by the probability, and that would give us, also, we know that the variance of x is just sigma squared. So if you're given a probability distribution, you can find the average, the mean, by this formula. You can find the standard deviation by this formula. And that formula actually breaks down into some nicer formulas depending on what distribution we're looking at. Sometimes x has a predictable distribution, and we're going to talk about one of them today. Let's talk more about counting. Okay, so let's look at a definition. For non-negative integer n, we define so-called n factorial by, there's a formula, this is the notation, it's n with an exclamation mark. Does anyone know what that is? Yeah, but like, how is it defined?
N factor.
No. So it's the product of all integers from 1 up to the number n. N minus 1 times n. Right? So example, you see 5 factorial is really just 5 times 4 times 3 times 2 times 1, which I think is 120. 4 factorial is just 4 times 3 times 2 times 1, which is 24. 3 factorial is 3 times 2 times 1, which is 6. 2 factorial is just 2 times 1, which is 2. 1 factorial is just 1, which is 1. 0 factorial is actually 1 by convention. Basically, this follows a pattern that is mathematically consistent, so we just define that to be 0 factorial. It's also 1. So that's what a factorial is, and why do we care? N factorial equals the number of ways to permute or arrange n objects. So it's actually a counting tool. If you want to arrange things in order in some way, n factorial will tell you the number of ways. So, example, if you have 3 objects, call them x1, x2, x3, then these can be arranged. These can be arranged in 3 factorial equals 6 ways. So it's literally a quick way to count. How many ways can we arrange something? So you can have x1, x2, x3. You can have x1, x3, x2. You can have x2, x1, x3. You can have x2, x3, x1. You can have x3, x1, x2. You can have x3, x2, x1. There are 1, 2, 3, 4, 5, 6 different ways to rearrange 3 objects. Right? In fact, the factorial actually tells you the number of ways to rearrange things. Right? So that's why it's useful. One of the reasons why it's useful, there are other formulas that uses it. So basically, if someone says, how many ways can you arrange 4 objects? Well, there are 24 ways you can arrange 4 objects. The idea is, we actually use the multiplication rule here. If you have 3 objects, then you have 3 choices for putting something in first place. Once you chose that, there are only 2 choices for putting something in second place. And then for the third place, there's only 1 guy left. And this can generalize to higher things. So because of this, they apply this multiplication rule principle. They just developed a function that sort of counts this. And so you just know now, if you need to arrange n objects, n factorial is how many ways you can do it. Right? So this will help you to count things. There are going to be times when we have probabilities when the order matters, and we want to know how to count how many orders there are. So the n factorial is going to be useful here. So we're just a way to get more efficient with our counting, and we're going to even go further. Definition. This is called the combination. NCR is the notation. You might also see NR, or you might also see CNR. Different calculators will have different notations, etc. Okay. So the combination is the number of ways to choose R objects from N objects. It's given by R is equal to n factorial divided by R factorial times n minus R factorial. example, if I say 3 choose 2, that's the same as 3 factorial divided by 2 factorial times 3 minus 2 factorial, or it's just 3 factorial over 2 factorial, which is just 3. Okay. And that's basically the number of ways you can pick 2 objects from a list of 3 objects. Right? So if I have 3 objects and I want to pick 2 of them, how many can I pick? I can pick object 1 and 2, or I can pick 1 and 3, or I can pick 2 and 3. Right? There are 3 ways to choose 2 things from 3 things. Right? So that's an efficient way to count a choice of a subset from a general set. How many ways can you choose a subset of size R from a set of size N? Also notice that, note 3 choose 2. The idea is you can actually put the factorial of the one on the bottom, you start the factorial of the one on top, and you stop it in the same number of places. So that would also give you 3. Or let me show you one that you might see easier. 7 choose 3. It would actually be the same as taking 3 times 2 times 1. That's 3 places in the denominator. So you start the factorial for 7 in the top, but you stop after 3 places. It's actually equivalent to that one. Right? So you can say 3 times 2 gives you 6, so this is just 7 times 5, which is 35. It's also on your calculator, so you should know how to do it. If you have, say, calculator, look for the symbols NCR or CNR or NR, etc. Your calculator will have one of these symbols here. Who has a TI? No, the TI-89 or. So if you have a calculator like this one, how you actually find it is on TI-83 or similar. Enter n, you'd enter the number n, then press the button here is math. Then scroll to PRB, which stands for probability. So functions that use in probability often will be under here. So you'll just, in the top you have math, num, complex, probability. You move over to the side to probability, and you'll realize the third choice has this notation, NCR. You literally just punch that in, press NCR, which is choice 3. Then enter the integer R, then enter. So different calculators will have different things, but that's sort of how you do it on a TI-83. Okay, so on this calculator, this is also this is a TI-36. You'll see right here, there's actually the button for NCR, if you look at it there. So that covers factorial, NCR, and NPR. NPR is sort of the permutations, cutting off at a certain point. But yeah, some calculators will have that button just right on the interface. But TI-89 is actually hidden in the math menu. So if you have that calculator, that's how you get to it. So if you So basically, just want to make sure you know how to do it on your calculator. So to find 7, choose 3. What you do is you plug in 7, press math. You guys can try it to make sure you know how to do it. Scroll to probability. Then you'd press NCR, which is the third choice. Then you'd press 3. Then you'd press the equal button. And the answer should be 35, if you actually try it. Other calculators will have this button like right away. You usually will enter the first number, then you press that button, then you enter the second number. Okay, so try to make sure you know how to do it on your calculator, so you don't have to do this formula all the time. If you have a calculator, a scientific calculator can do this for you. Just know how to enter it. So try to figure it out. If you can't figure it out, then you can ask me and I'll talk to you outside of class about it. Okay. But this is a very important formula. It's called the combination. It tells us the number of ways we can choose a certain number of objects. So, do I have an example? Okay, yes, I do have an example. So here's an example. There are 10 people eligible to be chosen for a committee of how many people did I say? 4 people. How many possible committees are there? So basically you have 10 people that you can put on a committee, but you only want the committee to have 4 people. So basically the question is, out of these 10 people, how many groups of 4 can I possibly create, right? If I pick the first 4, or the last 4, or just randomly pick 4 people, how many different committees can I come up with, right? Basically, this is a problem of being able to choose 4 objects from 10 objects, right? If you think of the people as objects. Right? So, all things considered equal, if everyone has an equally likely chance of being chosen and you're not discriminating, how many possible ways can you pick a committee? The answer is 10 choose 4, which you can plug that in your calculator. What answer would you get if you tried that? 210, right. So make sure you can actually do this in your calculator. You should get 210 as the answer. Right? There are 210 possible committees that we can make. Right? So if I have 10 people and I want to choose 4 of them to make a committee, there are 210 possible groups of 4 people that I can choose from 10 people. Right? If I choose a different set of 4 people all the time, there are 210 ways I can do this. Yes?
But that's assuming that the positions are set, like rotating each position.
Oh, one thing, let me just mention that. For combinations, for NCR, order does not matter. Right, so if I pick a group of 4 people and I sort of arrange them differently, this guy doesn't count it. Right? It considers it, once you pick these 4 people, that's a group. Doesn't matter what order you put them in, that's a group. It's unique upon the items chosen. If you want to care about order, then you'd use the NPR. Right? That's if you know you want to pick a committee where someone's the president, someone's the vice president, someone's the secretary, someone's the treasurer. Right? You have literally stations that people can go in order of importance, then you would not choose this. For NCR, order does not matter. That's actually a very important distinction. NPR gives, and it's very similar to get it in your calculator as this. It will usually end up in the same menu or the same place. NPR gives the number of ways to choose R objects from N objects in a certain order in a way that order matters. The formula here is sort of simpler. So if you had something like 5p3, it's just going to be 5 times 4 times 3. Right? You start off the factorial with this one, and you go up to the number of places of that number. Right? So there are 5 possible people you can choose for the first position. Once that's filled, you can only choose 4 for the second position. Then only a possible 3 for the third, and so on and so forth. But it stops there. So this is the one where order matters. For the combination, though, order doesn't. I just want to pick a group of 4 people. I don't care how you arrange them. Then this would be the way to do it. If you want to order them in a specific order, then 10p4 would be the way to do that, which would give you a different number.
There are a lot of really cool examples I could tell you about this, but
You probably won't need it. Like other probability courses would give you questions like, oh, you know, there's this group of 10 people who want to choose a committee of 4, but there are 2 people who are not friends and they're not speaking to each other and they refuse to serve on the same committee. How many committees of 4 people can you choose so that these 2 people do not work together? Meaning you pick either one of them or none of them, right? And there are different ways to count that, but I won't get into that. You don't need to count anything that sophisticated in 209. Usually you want to just count stuff where you can pick something where either order matters or it doesn't. And the question will usually make that clear. With that in mind, now we can talk about the main thing I did want to talk about today is very important discrete random variable. We're still in the discrete random variable case. It's called the binomial distribution. So the nice thing about random variables is, I know last time we were doing this, I was just giving you a table and throwing in these random numbers, and sometimes you find this through experimentation or statistics. But there are actually situations where there's a formula that will generate the probability distribution where we know if something falls into this category, the probabilities are set, they're understood. We can actually have a formula to write them down. The binomial distribution is one of the most important ones. So let's talk about that. Guaranteed to come on a test or a final. So it's something you must know. Suppose we have this situation. One. Some experiment or trial is repeated n times 2. The outcomes of each trial are independent. 3. There are only 2 kinds of outcomes. success and failure. It's how you often hear them referred to. Usual notation is let P be the probability of success happening, and Q equals 1 minus P is the probability of failure happening. So only those three situations. So we're in a situation where we're repeating something n times, some experiment, some trial n times. The same thing is being repeated n times. Each outcome is independent of all the others. And there are only two kinds of possible outcomes. Then, if we let x equals the number of successes, then x is a binomial random variable. Probability of k successes is given by this formula. So, this situation, whenever you see this happening, it means that the number of successes is a binomial function. Binomial, the bi, is what says there are two kinds of outcomes. Right? So, they won't always mention that something's binomial. It's something you should recognize by reading the problem. You have to read a problem and realize these three situations are being fulfilled, therefore I can think of it as binomial. It becomes a systematic way to solve the problem once you realize this. And these kinds of situations shows up a lot more often than you think. Pretty much anything that would have a yes or no answer is binomial, right? Once it's independent and you're repeating the same thing. So we've done situations where we flip coins, right? Let's say you're flipping a coin a certain number of times. You've done examples like that. You flip a fair coin 3 times, right? That's an experiment. You're doing the same thing 3 times, n is 3, right? Each outcome is independent in that case, right? What the result of one coin flip has nothing to do with the result of another coin flip. And there are only 2 possible outcomes. You either get heads or tails, right? So flipping a coin is a binomial, it gives rise to a binomial distribution, right? So you can define, okay, we want to count the number of heads, so you can define getting a head to be a success, getting tails to be failure. And so if I say, what's the probability of 3 heads? It becomes a binomial distribution problem, right? And I would just plug in k equals 3. Clearly here, k would be 0, 1, 2, all the way up to n, possibly. Right? You can have no successes, the thing just doesn't happen, or it only happens once, or it happens twice, or it could happen all n times. Right? But basically anything that has 2 possible outcomes, all independent, it ends up being binomial. So for example, flipping a coin. There are other things that inherently they don't have 2 possible outcomes, but you can still think of them as binomial. For example, rolling a fair die. Right? I could say, okay, if you roll this die and you get a 3, then I pay you $1. If you get anything else, you have to pay me $1. Right? In that situation, the die has 6 possible outcomes, but really I can think of it as 2. You either get a 3 or you don't. Right? Once you can think of something in 2 possible outcomes, you're doing the same thing over and over. You roll this die 3 times. Right? If you get a 3, that's success. Get anything else, that's failure, right? Obviously rolling the dice is independent. So you're repeating something, independent, only 2 possible outcomes. It means you can think of it in this way. You can automatically know what the probability is. It's not something you don't have to like count situations anymore. We've actually figured out this will be the probability. Right? Moreover, we're going to do some examples. Moreover, I'm not going to derive it, I'm just going to tell you. It can be determined that mu equals the expected value equals n times p. Sigma equals the standard deviation is the square root of n p q. That's going to be important later.
I have one example here, but I'll probably go back and tweak the other example we did and show you how things can be different.
So we'll probably just do 2 examples and then I'll see if you guys have questions for the test. Oh, obviously the variance is just the square of this. Let's see. Example. Probability A. He makes all 10. B. He makes between 3 and 5. Inclusive. C. He makes exactly 2. For D, he makes at least 1. So this is a situation. We have a basketball player that we've looked at his stats, and he makes 70% of his shots on average, right? So if you want to sort of make some predictions, if you want to bet money on how many shots you'd make out of 10,
and you want to know what the chances are of you actually winning the bet, it turns out it's binomial. We're assuming all shots are independent. In reality, this probably would not be true, because if you lose a shot, then your ego gets damaged, and you're actually more likely to miss the next one. But let's pretend that he can just shake off whatever happens, and he shoots with objectivity all 10 times, right? So we're assuming here we have independence, and he's going to make 10 free throws, right? So he's going to just shoot the basket 10 times, meaning he's repeating the same experiment. He's doing the same thing over and over 10 times, right? There are two possible outcomes here, right? He either makes the shot or he misses, right? And they're all independent by assumption. So it means we have the three conditions fulfilled for a binomial probability. Right? So now when you get asked these questions, you don't really have to worry about a lot of things. You can actually just go straight to the formulas and get to the answer quickly. First, I want you to appreciate how difficult this could be without this formula. Look at part B, for example. Between 3 and 5 shots. Can you imagine how many ways he could make somewhere between 3 and 5 shots? Just look at how many ways could he make 3 shots, right? There are 10 possible options. He can make the first, the second, the third, or the first, the third, the fifth, the first, the third, the seventh, or the second, the sixth, the 10th, right? When you start counting all the ways that he could only make 3 shots, that's enough of a headache to count all those possibilities, right? This, nice formula, you can get it right away. I need to know how many ways you can make 3, plug in k equals 3. And done. It will literally count all those ways for me, right? It makes counting very efficient when things can be chosen. It's sort of like you're choosing how many possible ways he can make 3 shots out of 10, right? And that's where the combination comes in. That's the guy that tells you how many things you want to pick out of what total number, right? These guys end up telling you the probability of each situation, right? So k is the number of successes. This means if they're all independent, we can multiply the probabilities, right? So if he makes k things, the probability of making it is p, so you literally multiply p by itself k times. Then you'd multiply him missing by the rest of the time, right? And this is going to tell you how many ways you can actually choose that. Right? So this is a really nice formula, and it allows us to get to this question, actually solve this problem without too much headache, because like a tree diagram or any other thing that we've done so far, this would be a major headache. Right? But now, armed with this formula, it's actually not that bad. It's just a matter of plugging stuff into your calculator. So let's actually go through this problem. So here, first, let's identify our variables. What is n? What is p? What is q?
N is 10, p is 0.7, and q is 0.3.
Right? Which is 1 minus 0.7, right? It's the opposite. Another thing I want you to appreciate is notice that I never mentioned the word binomial here, right? It's just something you should know based on those 3 categories. You're always looking for something like that to happen, right? Something, there's something being repeated, there are only 2 outcomes, they're all independent. It's just something that's always in the back of your mind when you're reading a probability problem, because it's one of the things we have a nice formula for. So once we figure out, oh, this is binomial, right? There are only 2 possible outcomes. He either makes the shot or he doesn't. They're all independent, and he's doing the same thing over and over, right? This is binomial. So it means then I need to know what all these variables are. I need to know my n, my p, my q. Now let's look at part A. How many successes do I want? We want k equals 10 in this case. The probability, so first let's define our variable. Let x equals the number of successful shots, or number of shots he makes. In part A, we want k equals 10. This means the probability that the number of shots he makes is 10 is going to be 10, choose 10, 0.7 to the 10, 0.3 to the 10 minus 10. Now if you plug this into your calculator, 10 choose 10, how many ways can you choose 10 objects from 10 objects? There's only one way, right? That's going to be a 1. This is just going to give you 0.7 to the 10. This is going to give you 0 power. That's also going to be a 1. So this is actually going to be 0.7 to the 10th power. Another thing I want you to appreciate here is based on what we've done before, this is consistent, right? We have independent events. The probability at each stage is 0.7. How do you find the probability of making the first, and the second, and the third, and the fourth? You multiply them all. So this actually does make sense to us. Right? But thinking of it as a binomial is actually consistent. I don't have a calculator. It does that. Is that a nice one?
0.0825.
0.2825.
0.2825.
Wow. Right. So the chances that he'll make all 10, about 3%. I mean, to be generous, 2.8%. So if you know someone makes 70% of their shots and you want to bet that they make all 10, you got a 97% chance of losing that bet. It's not a bet I would make. I mean, like I said, it's probably not independent. Maybe he gets the first few shots and he just gets in the zone, but his psyche, someone else's psyche is not something you can bet on. If you want to be objective, it's not a bet I would take. So there's actually just under a 3% chance that he will make all 10. What about making between 3 and 5? Inclusive. Means he either makes 3, or he makes 4, or he makes 5. See, this is what we want. How do you think we do that one?
And the probabilities of 3 and 4 and 5.
And what do we do with them? Probability of 3 plus the probability of 4 plus the probability of 5. Why would I add them? It's mutually exclusive and there's an OR. How do I know they're mutually exclusive? Well, if he only makes 3 shots,
He can't make 4.
then he didn't make 4, right? Right? These are all mutually, they can't happen together. You can't say he made 3 shots and he made 4 shots. No, it's one or the other, right? So these are actually all mutually exclusive, right? And in a binomial probability, it turns out that's always the case. If you have some number of successes, you can't have some other number of successes. That was just a number. So the binomial is another case where we have both independence and mutually exclusive being satisfied at the same time. So and we can think of as multiply, or we can think of as plus. And so what we have now is we have formulas for each of these. So this is the probability that he makes 3 or 4 or 5. This guy would be 10 choose 3, 0.7 to the 3, 0.3 to the 7. By applying that formula, we have 4. This would be 10 choose 4, 0.7 to the 4, 0.3 to the 6, or 10 choose 5, 0.7 to the 5, 0.3 to the 5. And what's that?
53.00.
In the final answer?
Oh, no.
This one
Yeah.
is 0.009.
009.
Okay, let's keep things 3 decimal places. What's the next one?
0.037.
0.037. You guys should be trying this on your calculators to make sure you know how to use them. Okay, don't just watch me writing, make sure you're actually trying it.
103. Okay, so in total,
Zero point 149.
0.149. So the chances of him making between 3 and 5 shots is actually a little better. It has about a 15% chance. And this saves us from counting, well, how many ways can you make only 3? And then only 4, and then only 5, and then you add them all up together. You'd be there forever. We're very close to it. Let's see. What did I want? He makes exactly 2. What's the probability he makes exactly 2? Well, here, you simply want k equals 2. Probability of x equals 2 is 10 choose 2, 0.7 to the 2, 0.3 to the 8, right? Or 10 minus 2. That is. Zero zero one. Yeah, I wouldn't bet on him making exactly 2 shots either, right?
What's the sub's trying?
So there's a higher chance of him making all 10 shots than 2.
Yeah.
Really?
So you know he'll probably make more than 2 shots.
What?
I think I
So
did
you
it
could
wrong.
bet on him making more than 2 shots.
More than 2, yeah, that would actually be probably a good chance, because that would mean 3 or 4 or 5 or 6. You're adding up all these probabilities. And we already know just making exactly 5 is already a 10% chance, so it'll probably add up a lot. Yeah. So yeah, more than 2 shots would actually be probably something you might bet on. Not saying the exact number, but knowing that just more than 2. Okay. He makes exactly 2. What's probably he makes at least 1? So in part D, we want the probability. What does at least 1 mean?
More, 1 or more.
Huh? 1 or more, right? At least means greater than or equal to. Right? So basically that would be the probability of 1 plus the probability of 2 plus the probability of 3 plus all the way up to the probability of 10. And then of course we're going to just plug this into our calculator, right? Okay, go ahead, do that. I'll wait.
There's no shortcut.
I was wondering if someone's going to ask. Can someone tell us what the shortcut is?
You just find 1 and then 1 minus that, right?
Use the complement, right? I'm not going to want to plug this in 10 times my calculator. Notice that this is just 1 minus the probability of making less than 1, which is basically 1 minus the probability of making 0, right? Basically, all the options are he either makes none, or 1, or 2, or 3, or 4, right? There's only one possibility that's omitted here,
So it's just 1 minus that one possibility. So basically, 1 minus the probability that he misses all of them is basically what I'm going to try to find. Which is usually, it's going to be the probability of losing to the 10th power. Let's see if we actually get that. This means he makes none. 0.7 to the 0. 0.3 to the 10. Turns out this is going to be 1. This is going to be 1. So it's just 1 minus 0.3 to the 10. And what's that roughly? 0.999.
0.999. You could bet on that.
You can definitely bet on that. He has a 70% chance of making a single basket. What's the probability he'll make at least 1 out of 10 shots? Pretty good. That's an argument for being persistent if there ever was one. Just keep trying. You'll succeed at least once. Well, depending on the original probabilities. Let's see here. Maybe one more where I want to tweak that. Because this is actually very typical. They actually sort of repeat the same sort of question, but they just change the numbers almost every semester. The blood example, we're talking about someone donating blood and we need a certain blood type. Turns out we can think of much more complicated situations now that we have the binomial theorem, or the binomial probability distribution. So that was the one where I told you what the probability of A and all that stuff was. Probability of having blood type A was 0.4. Blood type B was 0.1. Probability of blood type O was 0.45. Probability of blood type AB was 0.05. Probability of having RH plus having that protein is 0.85. Probability of not having that protein is 0.15. The probability that someone could donate to a person with type AB and RH plus. We actually computed that. That was what? Someone can tell me, so I don't have to do it again. What? 425. All right, so there's a 42.5% chance that someone could randomly donate. You randomly pick someone off the street that they can actually donate some blood to someone with an AB blood type and RH plus protein factor. Right? And we did the questions where I asked, what's the probability that a random person could donate blood to the person? This was it. And we also did, if 10 people walk into the blood bank, what's the probability that at least one can donate to the guy? That was a very easy case because we just did 1 minus the probability if no one could donate. And so now we can actually ask more sophisticated questions. I could, for example, ask you, suppose the man needs 3 units of blood. Each person can donate 1 unit.
if 10 people donate, he will get the blood he needs. Now, first, appreciate how difficult a problem this is, especially if we're using our old techniques. I'll tell you about that later. Right? So the guy now needs 3 units of blood, not just 1. Right? What's probably that 10 people randomly donate, he will get the blood he needs? Well, let X equals the number of people that can be a donor. What do we want here? The probability of what?
You get 3 pints of blood out of 10.
So if we want the probability of X, what? Describe it to me.
X3.
Don't you want probably that 3 out of the 10 people can donate 1 that each person can donate 1 unit. So you would need 3 for him to be able to get this.
Right, but think of all situations where you can actually get that. Does X equals 3 cover everything?
No, actually 4, 5, 6, 7, 8.
Yeah, you could have more. That's not a problem having too much blood, right? You'd want at least 3, right? So basically, if 10 people walk into this blood bank, how would this guy get the blood he needs? At least 3 have to have it, right? So I can have 3 people, minimum has to have it for him to get the blood he needs. But if there are 4, there's no problem, just go get it, or 5, or 6, or 7, right? So basically, this comes to a problem, down to a problem of figuring out what is probably that 3 or more people will have his blood type, or a blood type sufficiently close to his that they can donate. Right? And again, think of the situation where exactly 3 could donate. You'd have to figure out, well, out of these 10 people, maybe it's the first and the second and the third, or the second and the fourth and the 7th, or the 10th and the 9th and the 3rd, right? How many ways you can pick 3 people out of 10 people to donate to this guy? There are a lot. But with the binomial theorem, it's not that bad. We don't have to think so hard. So what would this mean? Basically, this is probability of that 3 or 4 or anywhere up to 10 can donate. Do we want to put that into our calculator?
No.
No, we do not. Because we're in a test and we're running out of time. So what is the opposite of this?
1 minus P of 2 plus P of 1.
Well, less than 3.
Yeah, it's less than 1, 2, or 0.
Right, so it's probability of X less than 3 is the opposite, which means, yeah, someone said 1, 2, and 0. The first person who's mentioned forgot the 0. So it's possible that no one can do it, or only 1, or only 2. So instead of computing like 7 probabilities, I can do this complement probability and only do 3. Still slightly annoying to plug in your calculator, but it's better than plugging in 7. So this is going to equal 1 minus probability of 0. So it's 10 choose 0. That number 0.425 to the 0. What's 1 minus 0.425? 575?
Yeah.
To the 10 plus 10 choose 1, 0.425 to the 1, 0.575 to the 9. Plus 10 choose 2, 0.425 to the 2, 575 to the 8. And what's that answer? Don't forget, when you add these all up, you have to subtract the result from 1. Someone get the answer already? Did you get it?
18697.
0.86 8697. So there's an 87% chance he'll actually get the blood he needs. It's not bad. Not great, but it's not bad. So when you're faced with a binomial probability, the main hurdles that you have to overcome are, one, you need to recognize when it's a binomial probability, because they're not going to always tell you. It's very unlikely that they will tell you. Right? So, and what you're doing is you're always going to try to make sure those three conditions are fulfilled. You're repeating the same experiment over and over. There are only two possible outcomes that are independent of each other. Right? And they're independent. So you're repeating the same thing, only two possible outcomes, all outcomes are independent. Whenever you have these three things, it's binomial. You can use this one, and it will cut down on the amount of counting you have to do and the amount of arrangements you have to think of. The next hurdle that you'll have to jump over is to figure out what you actually want. To be able to phrase the probability that you want in a formula like this, so you know which ones you have to add up or count. So being able to say, oh, I want 3 or more here is actually a very important part of the problem. The rest of it is just mechanics. Once you figure that out, then it's just punching it into your calculator and just going through the motions. But those are the two major hurdles. First, recognizing what it is, recognizing what probability you're being asked for, and the rest should be more or less straightforward. The first two would be the hardest things to figure out. Are there any questions on this? Does everyone seem to get it? Yeah. Okay. Are there any questions on chapter 11? Well, everything for the test, I guess, is everything. The test will be on. Never find the syllabus when I need it. I think chapters 7 through 11, so 7, 8, 9, 10, 11. So that's going to cover all the way from histograms, when we were talking about measures of central tendency, the different averages, mean, mode, median, range, standard deviation, how to do a box plot, how to do the bins with the frequency and estimate the mean, mode, standard deviation, scatter plots and making regression lines, using them to predict stuff, and probability. We won't include what we did in chapter 13, everything up to when we did conditional probability. So
there's anything you need to clear up, you can ask me. Yes? And did anyone actually start the review problems from the exam? Because you can probably ask me about those. Those will be more like your test. So we're doing chapter 11. One more. Maybe after this we'll do some stuff from the exams. Number 9, what did that say? Does anyone have the book?
So you have a bowl of like 3 red balls and 5 black, and they're not replacing them.
So we have bowl, 3 red balls, 5 black.
Yes. No replacement.
No replacement. Okay, what were we asked for?
At least one black ball out of.
Wait, how many do we choose?
3 times. 3.
You choose 3?
Choose 3.
And part A is
At least one black ball.
at least 1 black. Is there part B?
Yeah, at least 1 black and 1 red.
At least 1 black and 1 red. Is there a 3? C?
No.
So that's it. Okay. Can anyone tell me how to do A? Also a very typical question, this choosing stuff, choosing balls from an urn or a bowl or something like that. It's a very typical problem to do. Usually on the finals, they ask you to choose 2, but it's not a big stretch to ask you to choose 3. But usually they leave it at 2. But it's a very typical kind of problem. If you know how to do this, you'll be in good shape. The blood donation problem is also a very typical kind of problem. Okay, how do we figure out the probability of at least 1 ball, black?
So there's no replacement, so the first time you have 8 opportunities, and so it would be 5 out of 8 to choose. 1 ball. 1 black
Oh,
ball.
so we're doing the probability of at least 1 black.
That's not what I had as number 9. I have the probability of 3 black.
That's a black each time.
Yeah,
Yeah, black each time.
so 3 black balls.
Black, yeah.
This said black each time?
Yeah. How do we-
Oh,
Sorry. I must have written that.
black each time. Okay, that's a very different situation. So basically we want 3 blacks. Okay, so yeah, we have 8 total choices as she said. There are 8 things in this bowl. 5 of them are black. So to get 3 blacks, there's only one way. You have to pick 3 right after the other. The first one has to be a black, and the second, and the third. The and means we multiply, so the first one is
5 over 8.
5 over 8 times
4 over 8. Because you're not
Sorry, 4 over
replacing.
7.
Or 4 over 7. Yeah, because you're not.
4 over 7, right? Because
Yeah.
we're not replacing. So you take out, there are 5 ways you can choose out of 8, but you throw away that ball, so now there's 7 left, and there are only 4 blacks. And then you go again, now it will be 3 out of 6. Because then you throw away that one, and now there are only 6 left and only 3 blacks left. So that was what?
0.179.
0.179. Right, so just about an 18% chance that all 3 will be black. Okay, B. At least 1 black and, this was and. At least 1 black and at least 1 red. Okay, how do we do that one?
You compliment.
That would be the complement. So probably of at least 1 black and 1 red is equal to 1 minus the opposite probability would be no black or no
red.
So this would be the probability of no black, or would translate to plus here, they're mutually exclusive, or the probability of no red. And what's the probability of not getting a black?
3 out of 8.
It's 3 out of 8, which means you have to pick the red first. 3 out of 8, then what?
2 out of 7.
2 out of 7, 1 out of 6, plus no red means we pick all 3 black, which we just repeat there. 5 out of 8, 4 out of 7, 3 out of 6. And that was what?
One minus 0.196 or 66 over 336.
66 over 336.
You have one minus that.
1 minus this.
Yeah.
Yes.
So it would be what?
0.804.
0.804. So there's roughly an 80% chance we'll get at least one or the other. Any other questions? Was there any one on the exam that you guys tried that didn't get?
Row number 4 for 2008 spring. Number 4.
On the same problem, if you have like 10 red or 20 black, could you use binomial?
It would depend on how the question is phrased. Like if you can phrase it in a way to get either black or not black, then sure. But phrasing this one that way would be actually really difficult. It probably wouldn't be worth your time to try to figure out that situation to phrase as this. But this one you could think of it as binomial, sure. Right. The probability of getting a black versus, let's see, no. This, you couldn't do this as a binomial. Anyone see why? Yeah?
Is it because it's not being replaced?
Because there's no replacement, which means your probability of success actually changes at each step. So that's why you couldn't think of this as a binomial. If you had replacement, then you could actually think of this one as a binomial. But yeah. So number 4, I wouldn't really ask something like that. So number 4, you're given 3 scatter plots and they say, oh, arrange it in order of increasing R. Basically the idea is you try to draw straight lines. And if something is very close to a straight line, then if it's negative slope, it's very close to -1, which means it will be the smallest. If it's positive slope, then it's more positive. And if this one is scattered here, the R is probably close to 0 here, probably close to -1 here, slightly positive here, so you would arrange it that way. This would be, this is for the smallest R, this would be the middle R, this would be the largest R. Sort of. I wouldn't ask something.
How many points the question? 6?
That was like 4 points question. I wouldn't ask something like that. Yeah.
Oh, no, no.
2008, number 9, are you gonna have that?
Are you 2000? Is this 2008?
It's everything in there.
It's relative frequency.
2008. Problem 9.
Yeah. Are those on this test? It's relative frequency. You had it or not?
Yeah, that's a fair example. You want me to go through it, or were you just asking if I asked
Yeah, you
something?
go through it.
So we have 10, 25, 35, 40, 25. All right, so here's where they gave you basically the frequency table in terms of bins. So I know there are 10 bulbs that last somewhere between 800 and 900 hours, right? We don't know exactly which, we just know that there are 10 of them that appear in this bin. So for part A, we need the relative frequency. So let's just put it in this table, relative frequency. So we have 135 bulbs in total, randomly selected, which means the relative frequency here would be 10 out of 135, 25 out of 135, 35 out of 135, 40 out of 135, 25 out of 135. That would be the relative frequency, and it says, based on the data, prepare a relative frequency histogram. Histogram. Show hours overnight. So this is relative frequency. We have 1, 2. 5 categories, so we can actually be either in the 800 to 900 bin, which I can mark by the center number, 850, 950, 1050, 1150, 1250. And I can have 10 out of 135, which you can write the decimals here if you'd like. In particular here, 25 out of 135, 35 out of 135, 40 out of 135. So for the first one, it's a 10, so we go here. Second one is a 25, so we go here. Next one is a 35, so we go here. Next one is a 40, so we go here. And the last one is a 25, so we go there. So that's the histogram. Estimate the median. So, what's the median here? What position would the median be in? This would occur in the what position? We have 135 numbers in total.
67.5.
Right, so 67.5, let's say it's 68. So we have to figure out the 68th number. This is blank steps into the spin. Okay, where would this actually put us to get to the 68th number?
1,002.
We get the first 10 here. This is the first 35. Here would bring us to 70, right? Which means we have to hit 68 before that, right? So how many are in here? There are 35, which means how many steps into here we need to take? 33. This is 33 steps
into the 1000 to 1100 bin. Okay. So here, this tells you the number of steps. How do you figure out the step size?
1100 minus 1000.
All right, so remember this is the bin length over frequency, which means it's 1100 minus 1000 over 35. So this is what? 0.86? 2.86. This means the median equals left endpoint plus number of steps times step size. The left endpoint of that bin is 1000 plus the number of steps is 33 times the step size is 2.86. So the median number of hours would be, what is that? It's 1060, close to 1090 something. 1094. All right, so the median number of hours that one of these bulbs will last is 1094 hours. How would you estimate the average? Here's the table, so this is called 9 part C. So how do you estimate the average?
10 times 850.
Right, so by this they mean the mean average. They say compute your answer to 3 decimal place. So here, the mean would be approximately equal to, right, you assume each part takes on the average value in the bin, and these are how many numbers that take on that value divided by the total number of numbers. So it'll be 10 times 850 plus 25 times 950 plus 35 times 1050 plus 40 times 1150 plus 25 times 1250 divided by the total number of numbers.
1083.3.
1,000?
83.
83.3.
0.3.
So that's the average number of hours. And this was the median number of hours. Approximately. So study of classroom size discovered that in Shepherd Hall, 20 classrooms seat 25. Ten classrooms seat 30. 8 classrooms seat 35. 15 classrooms seat 40.
7 classrooms seat 60. 8. Mean number of students a classroom can hold. How do you think you'll do that?
How many classrooms divided by how many seats? Divided by times each other divided by how many classrooms total.
Okay. Maybe I should write it over here. Okay, so how would you do it? What's the formula you'd use? Well, there are 20 classrooms that can seat 25, right? So that's how many students you can seat in those 20 classes. 10 classrooms can seat 30, 8 classrooms can seat 35, 15 classrooms seat 40, 7 classrooms seat 60. The total is the total number of classrooms, which is 10 plus 20 plus 8 plus 50 plus 70, which is 60. And that was what? Right, we want the average number of seats per classroom, is what they're asking for. What?
35.
35. So the median how would you get to the median?
68 divided by 2.
50.
And you actually don't have to estimate here because these are actually the actual numbers. These aren't estimates or bins. So what's the situation we have here? There are 20 that can seat 25. So look at the number of students, the number of seats. So you have 25, 25. We're just listing all the numbers, 25. And there are 20 such numbers. The next step up is 30. So you have 30, 30. And we have 10 such numbers. Then we have 35, 35, 35. There are actually 8 of these numbers, all in line. There are 40, 40, 40. There are 15 of these guys. And there are 60, 60, 60. There are actually 7 of these guys. And we have 60 total, right? This means median equals the mean of the the 60th, the 30th, and 31st number. Right? So what's the 30th number?
30.
Oh, or the 20, I hit 10 here. He's the 30th number. That my median is actually going to be the average of these two. So it's going to be 30 plus 35 over 2. So that's 65 over 2.
32.5.
Which is
32.5.
32.5 seats.
Looks like the cover chapter.
7, 8, 9, 10, 11.
So los capítulos 9, 10, and chapter 13.
No, chapter 13 is not in it. Just the knife, probably before we got the probability distribution, is covered. Regression lines and all the stats stuff, the histograms and all that. Mean, median, mode is covered. Yeah. Let's see, 100. Yeah, so, yeah.